Precision mechanical measuring is an important skill in the workplace because manufacturing standards require that parts, components, and assemblies meet certain design specifications. If incoming or outgoing parts don't match or fit or cannot be interchanged, the quality of the product will suffer. A single small error can result in a returned product. To make sure that design specifications are consistently met, quality control standards must be maintained. Accurate measurements are required for inspecting incoming parts used in the manufacturing process. If an incoming part does not meet specs, the outgoing finished product will not meet its specifications either. Outgoing components and assemblies must also be measured. Analyzing data from large numbers of measurements of identical components can determine average dimensions and ensure that the customer is receiving a quality product. The measurements can be used in statistical process control, or SPC. Sometimes the gathered data can point to necessary design changes or changes in production techniques. Accurate measurements are also necessary for permanent record keeping. Keeping a record trail of accurate measurements can become an invaluable aid in servicing and troubleshooting components. Some sources of problems can be traced by examining the dimensions or fit of various parts or assemblies. Such a record, sometimes called a traveler, can be particularly valuable on reworked components or returned components with problems. In order to ensure that quality control standards are met, parts must be manufactured within tolerances. Tolerance is the maximum range or variation from specification which can be allowed without possibly impairing the operation or fit of a component. For example, a design specification of 9 units with a tolerance of plus or minus 1 unit would indicate that a part would be acceptable if it measured between 8 and 10 units. Measurements of a component's dimensions are taken and then compared to the values and tolerances shown on prints or specification charts. These measurements determine whether the object falls within the tolerance range. Because tolerances can be quite small, in this course we will be demonstrating how to perform precision linear measurements of surface dimensions. Linear measurements are taken along a straight line between 2 points on a surface, or between 2 surfaces. We can take several types of linear measurements. They include the length or width of an object's height, the thickness of an object, the depth of a hole or a step, and the diameter or distance in a straight line across a circle so that the circumference or rim of the circle is divided in 2 equal parts. Notice that there are 2 types of diameter measurements. One is across the inside of a circle, such as the diameter of this hole. This measurement is called an inside diameter and is usually referred to as an ID. The other diameter measurement, called outside diameter, or OD, is the distance across the outside of a circle or round object, such as the diameter of this dowel pin. Sometimes both the ID and the OD of an object must be measured. For example, a cylindrical object or rod may have a hole down its center. In this case, to get an accurate measurement of the thickness of the metal, the inside diameter, a measurement across the hole, must be subtracted from the outside diameter, a measurement from one side of the cylinder to the other. Each of these types of linear measurements is made using either the English inch measurement system or the metric system. In manufacturing and assembly applications in the United States, the inch measurement system is most commonly used. The inch measurement system uses the foot and the inch as the basic units of linear measurement. As you know, there are 12 1-inch segments in a foot. And the inch can be further divided into either fractional units or decimal units. Let's talk first about the divisions that are shown as fractions of an inch. This length represents 1 inch. 1 inch can be divided into 2 equal parts. Here is the 1/2 inch mark, If a half inch is divided equally, you get fourths, or quarters of an inch. 2 quarters make up 1/2 inch. 4 quarters equal an inch. The inch is further divided into eighths, 16ths, 32nds, and 64ths. Usually, 64ths are the smallest fractions into which an inch is divided. Here is just a quarter of an inch, which has 16 64ths. 1/2 has 32 64ths. 3 quarters equals 48 64ths. 64 64ths make up 1 inch. The inch can also be divided into decimal units. The decimal inch can be divided into 10 equal parts. Each of the 10 equal parts is referred to as 1/10 of an inch, written 0.1, then 0.2. Here is 1/10, 2/10, 3/10, and so on. Each tenth can also be divided into 10 equal parts. This results in the inch being divided into 100 equal parts, or hundredths. Hundredths are written as 0.01, 0.02, and so on. 1/100th of an inch, 2/100ths of an inch, and so forth. There are 10 hundredths in 1/10 of an inch, and 100 hundredths in 1 inch. Each hundredth of an inch can be divided further into 10 equal parts. This will create 1,000 equal divisions called thousandths of an inch, written as 0.001, 0.002, or 1,000th, 2,000ths, 3,000ths, and so on. There are 100 thousandths in 1/10 of an inch. So the decimal system method of dividing the inch allows more accurate measurements than can be taken with the fractional inch system. This is a decimal rule with each inch divided into tenths on one edge. On the other, parallel edge, the inches are divided into hundredths. We need to note that there is a particular way to identify decimal divisions of an inch as used by engineers, technicians, and assembly personnel. Rather than reading dimensions in tenths and hundredths of an inch, all decimal measurements are commonly described as thousandths of an inch. On this decimal scale, when the inch is divided into 10 parts, each part is called 100 thousandths of an inch, because there are 100 thousandths in 1/10 of an inch. Counting across, we read 100 thousandths, 200 thousandths, 300 thousandths, 400 thousandths, 500 thousandths, and so on. This measurement would be read as 700 thousandths. A measurement could be located at one of the 10 divisions between 100 thousandths markings, such as this one. This measurement would be read as 1 inch and 710 thousandths of an inch. We will be reading decimals of an inch as thousandths throughout this course. Expressing decimals in thousandths should become second nature. In manufacturing and assembly operations, there is sometimes a need to measure even more accurately. At times, measurements of increments as small as individual 10 thousandths of an inch are required. That's 10 divisions in each thousandth. Typically, however, decimals are rounded off to the nearest thousandth. Generally, if the measurement is halfway or more to the next thousandth, it is rounded up to that value, while if less than half, the value beyond is dropped. For example, 477 thousandths and 9 ten-thousandths can be rounded up to 478 thousandths. 477 thousandths and 3 ten-thousandths can be rounded down to 477 thousandths. Outside the United States, another measurement system, the metric system, is normally used. Parts are often manufactured to metric specifications, so engineering prints may also note specifications and dimensions using the metric system. In the metric system, the basic linear unit is the meter. which is slightly longer than 3 feet. For measurements longer than a meter, values are expressed as multiples of 10. For example, 1,000 meters is a kilometer, or kilometer. For measurements shorter than a meter, the meter is divided into 100 parts, or centimeters. The meter can be divided further into 1,000 equal parts, called millimeters. There are 10 millimeters to each centimeter. Metric measurements are commonly read only as millimeters, instead of as centimeters and millimeters. For example, 0.015 meters is expressed as 15 millimeters, instead of 1 centimeter and 5 millimeters. 26.5 centimeters is expressed as 265 millimeters, and so forth. Often, fractions must be converted into decimals and vice versa, or conversions between English and metric systems may be required. Decimal and millimeter conversions can be done with a calculator, but in most practical applications, a conversion chart is used. In manufacturing, these charts are printed on cards, labels, or engraved on the measuring tools themselves. Conversion charts often provide other information as well. This chart lists measurements in 5 different categories: fractional inches in the first column, decimal inches next to it, wire gauge sizes, millimeters, and tap drill sizes. Other charts may only show 2 or 3 of these conversions. Let's examine this fairly standard chart found in your study guide. To use this chart in converting fractions to decimals, find the fraction in the fractional inch column and follow across to read the number in the decimal inch column. For example, 1/64th equals 0.01563 inches, as you can see. This chart shows the decimal equivalents to 5 decimal places, more accurate than you will normally need. This number could be rounded off to 0.0156, read as 15.6 thousandths, or even rounded up to 16 thousandths. Certain fractions have easy-to-remember decimal equivalents. 1/4 of an inch equals 0.25, 1/2 inch equals 0.50, and 3/4 equals 0.75, or 750 thousandths of an inch. Along with the columns that indicate fractional inches and decimal inches, this chart has a column for the equivalent value in millimeters. For example, 1/2 inch in the fractional column has a decimal equivalent of 500 thousandths of an inch, and the metric equivalent is 12.7 millimeters. If a conversion chart is not available, there are 2 standard conversion factors for doing English to metric and metric to English system conversion. There are 25.4 millimeters in 1 inch and 0.0394 inches in 1 millimeter. To convert decimal inches to millimeters, you multiply by 25.4. For example, to convert 0.75 inches to millimeters on a calculator, enter the decimal 0.75, then multiply that value by 25.4. Don't forget to put the decimal point in the right place when doing conversions. The display will read 19.05. This is the metric equivalent of 0.75 inches. To convert millimeters to decimal inches, you multiply by another factor. Enter a value in millimeters, for example, 26 millimeters, and multiply it by 0.0394. That will give you your value in inches, which in this case is 1.0244, just over 1 inch. Now, let's apply what we've learned to the most basic instrument for determining linear measurements, the steel rule. Rules are used in many applications, even though they are not nearly as precise as the other instruments you'll be using in this course. They are designed for quick, relatively rough measurements. The engraved markings and numbers along the edge of the rule are called a scale. Rules sometimes come with different combinations of fractional and decimal inch scales as well as metric scales. Rules also come in different sizes and forms. 6-inch and 12-inch rules are common, and pull-out rules are available in several lengths. One of the most common rules is 6 inches long with scales for decimal inches on one side and fractional inches on the other. The fractional scale on this edge of the rule is divided into 30/2 of an inch. Each 1/8 of an inch is marked with the equivalent number of 30 These numbers correspond to the eighths divisions. The 16 30 marking indicates 1/2 inch. 8 30 equals 1/4 inch, and 24 30 equals 3/4 of an inch. On the opposite edge, each marking indicates 64ths of an inch. Once again, each corresponding eighth is marked in 64ths. As you can see, the numbers of the 30 and 64ths line up exactly. The indications for 1/2 inch, 16 30 and 32 64ths are right next to each other to form an easily recognizable reference point. Measurements are fairly easy to perform with the steel rule. The rule's edge is placed against the object to be measured, and the rule is lined up against the object. We read the division on the scale that indicates the length of the object. For example, we can measure the ID of this hole with the 64ths edge of this steel rule. The 0 indication on the rule is lined up on one side of the diameter, and the rule is placed across the hole. It should be swept from side to side to locate the maximum reading, which is the diameter. The scale indicates 42 64ths, which is 21 32 of an inch. On the other side of this rule, we can see inch markings represented on the decimal scale in tenths and hundredths. According to standard usage, each hundredth is read as 10 thousandths, and each tenth of an inch is described as 100 thousandths. 100 thousandths, 200 thousandths, and so forth. The marking indicating 500 thousandths is slightly longer, showing that it is also the 1/2 inch mark. To take a measurement using the decimal scale, once again we place the 0 edge of the rule against one end. The length is indicated here on the scale. This length measures 400 thousandths of an inch. Increased accuracy is achieved by using the other edge of the scale with markings down to hundredths of an inch. Remember, each hundredth equals 10 thousandths of an inch. Once again, every 100 thousandths is numbered. 500 thousandths is given a longer line to indicate it is the 1/2 inch line. However, between each number indicating increasing 100 thousandths, there are smaller lines that show each 10 thousandths increment. We can see that starting with 800 thousandths, for instance, there are 10 lines, each representing 10 thousandths. 10 thousandths, 20 thousandths, 30 thousandths, until we reach the next 100 thousandths indication, in this case 900 thousandths. The slightly longer marking at the 5th division between each number indicates 50 thousandths, halfway between the 100 thousandths marks. For example, this division between the 300 thousandths and 400 thousandths marks reads 350 thousandths. This division indicates 870 thousandths, since it is 2 lines past the 50 thousandths mark. As you can see, the 10 thousandths divisions can measure far more precisely than the 100 thousandths on the opposite edge. Measurements using a decimal scale follow the same procedure as a fractional scale. To measure the ID of this hole, dimension V on the practice assembly, the 0 edge of the rule is first aligned with the inner edge of one side of the hole. Then the rule is swept across the hole to locate the maximum reading, which is the inside diameter. Here, the scales indicate 800 thousandths of an inch. Metric rules are generally marked with the centimeter lines numbered. The 10 shorter divisions are millimeters. Remember, there are 10 millimeters in 1 centimeter. On this steel rule, each centimeter is numbered by 10 millimeters, 10, 20, 30 millimeters, and so forth. The longer divisions between centimeter marks indicate half centimeters or 5 millimeters. On this scale of the rule, the shortest, smallest divisions indicate half millimeters, 0.5 millimeters. This measurement is 30 millimeters, which can also be read as 3 centimeters. This measurement would be read as 25 millimeters, or 2.5 centimeters. This completes our introduction to measurements. Take the time to review the material in your study guide and perform the practice measurements on the assembly provided in the Precision Measurements Kit. The practice assembly print is an accurate representation of the practice assembly. You'll be using it throughout the course to locate dimensions on the actual assembly. Dimensions are labeled with letters and indicated by arrows pointing to lines extending from their edge surfaces. For example, dimension B is shown here on the print. On the assembly, the measurement to be taken of dimension B extends from here to here. Diameter and depth dimensions are designated by a single line with an arrow and 2 letters. For instance, here is dimension X, diameter, and dimension Y, depth. Dimension Q is located here on the print, so you would take the measurement between these 2 points in the assembly. In the next lesson, you will learn how to take measurements correctly with another type of device, the standard micrometer. This instrument is more precise than a steel rule and can give readings down to 1/10,000th of an inch.